Right, so welcome to this new video. So in this video what we are going to look at is first remind ourselves that last time we defined the micro-canonical ensemble. Okay, so here for example that would be an equilibrium, right, probability density given some energy here, and we have this quantity W of E. Now this quantity is actually called as well the degeneracy of the energy E. Okay? Now what I want to do is to compare it with a similar quantity we've seen in classical statistical mechanics, which is called the density of state. So degeneracy is actually not the same as the density of state. So to realize what the difference is between the two, what we are going to remind ourselves is the following. Well, so in quantum statistical mechanics, okay, we have the following thing. We have that Q and du of beta is equal to the sum over all possible states, alright, of exponential minus beta hi. Okay, so far so good. Now I want to connect this with the idea of density of state by saying the following. So what we are going to say is that we assume that the density of state in quantum statistical mechanics can be obtained from the fundamental connection. Okay, so there is a mathematical, like fundamental mathematical connection between Q and du of beta and G and du of E, and this connection is the Laplace transform. So it's Q and du of beta is equal to 0, integral from 0 to plus infinity d epsilon G and du of epsilon exponential minus beta epsilon. Alright, so this is a Laplace transform. Okay, so that's how I want to extract. So essentially, if I manage to put this expression here in a form like this, then I can extract what is a corresponding density of state. Okay, so that's what we are going to do here. So we start off with the same expression. So Q and du of beta is equal to sum over hi, etc., ai, bi, etc., exponential minus beta hi. And now I will write some identity, right? Exponential minus beta hi is equal to the integral from 0 to plus infinity d epsilon exponential minus beta epsilon delta epsilon minus hi. Okay, that's good. So then I can substitute this particular expression here into there. So this will give us the following: Q and DOF beta is equal to the sum over HI, then AI BI, and then I've got this integral from 0 to plus infinity d epsilon exponential minus beta epsilon, and then I've got delta epsilon minus HI. Now, what I know is that here I've got epsilon, here I've got epsilon, and here it's a sum over these guys, but there is no epsilon in here. So what I'm going to assume is that this is okay to swap the integral and the summation here. Okay, this is not super ultra rigorous, but this is something I'm assuming I can do. So then this is the integral from 0 to plus infinity d epsilon exponential minus beta epsilon, and then I've got the sum, and then HI, then AI BI, okay, and then delta epsilon minus HI. Right, we're almost there. Finally, I write something different. I write this particular thing as being 0 plus infinity d epsilon exponential minus beta epsilon. Then I write this as sum over all possible values of HI, sum over all possible values of AI, BI, etc. given HI, and then delta epsilon minus HI. And in fact, by the way, the delta here could be put over there. It does not really matter. And in the end, I end up with the following thing: 0 plus infinity d epsilon exponential minus beta epsilon sum over HI, and this thing here, this quantity, is actually W of HI, right? Because this corresponds to the sum over all possible states which have the value HI. So this is a sum, in fact, of W of HI itself, and then delta epsilon minus HI. But you see that it has the form that I want. So here I recognize that this is G and DOF of epsilon. Okay? So in the end, we get the final result that the relationship between the density of state, G and DOF of E, and the degeneracy is the following: sum over all possible values of the spectrum, the energy spectrum, and then WHI, and then delta epsilon minus HI. Alright, so that's basically where I wanted to end this particular note. It was a short video, just to show you that these things are slightly different from each other. They do resemble each other, but they are not exactly the same. So in the next video, what we are going to look at is one of the most, in fact, difficult example, in my opinion. This is a particle in a box.